Hi everybody. Sorry, if you're watching the recording, you would have seen 3 minutes of me leaving the room, then coming back. I've got to pause the recording. This week is going to be fairly light compared to the last two, and probably a bit shorter. But what I'm going to do for the videos is actually experimentally show what happens when you mix acids and bases, and the practical applications of this, and why acids are dangerous and why bases are dangerous. I'm going to start with an activity. So I want you to list 5 things that you think are acidic or base. Oh, sorry, 5 things are acidic and 5 things are base. So I'll give you 4 minutes to do that. So 5 things you think are acidic, 5 things you think are basic. Household items. And whilst you're doing that, I want you to think of why these things might be acidic or basic. What makes them acidic? What makes them basic? What makes something more acidic than something else? So 5 bases, 5 acids. And I'll stop talking. I'm not very good with silence. See if I can chat. So, if you can, because I don't want anyone's face popping up, put what you think are acids and what you think are bases into the chat. Give you a couple more minutes. Think household items, things you find around the house. It's Jacob, I can hear your mind working. Simple things around the house that are acids or bases. Yep, crystal, lemons, vinegar, and maybe cleaners. So I'm going to put these on the board as you guys put them up. kill this new black whiteboard marker in 10 days. Very upsetting. Anyone else? Acids and bases? Yep, Jacob, just think household items that you think might be acidic, as opposed to the actual acids themselves. So we've got lemons, vinegar, bicarb soda, Madison, got anything? I'll add mine in red. A complete blank. So, Jacob said sodium hydroxide. It's commonly known as, yeah, bases. So, sulfuric acid is used for cleaning. So, lemons contain citric acid. So, cleaning products, variety of different acids. Stomach acid is really, really acidic. If you vomit lots, if you have some kind of digestive disorder, it makes you vomit lots, eventually your teeth will erode away. And you'll get a constant burning feeling in the back of your throat. But acids, they're sharp tasting. Whereas bases tend to be soapy. They taste sour almost. So bases are slippery. So soap. So we know what acids and bases are around the house. So the ones I'll add in, soap and bleach. Again, I'm not sure about milk actually. Not 100% sure. Same with oil. I think oil might be basic. But again, soap and bleach. So sulfuric acid is a strong cleaning agent. A lot of drain cleaners are based on sulfuric acid. Pour the drain cleaner in, it breaks up all the hair that's blocking your sink and it goes through. Bleach is also a very strong cleaning agent, but in a different way. And we'll learn about why they're different and how they're different. Strong sulfuric acid can be just as dangerous as strong bleach, even though they're completely different ends of what we call the pH spectrum. And we will go through that. What makes an acid, and what makes a base a base. Share the screen again. I will shut the chat off if I see any more cross chat. No more fun. So, we have three definitions of acids and bases: the Arrhenius definition, the Bronsted-Lowry, and the Lewis classification. Goes from restrictive down to general in how restrictive their classifications are. So, we call Arrhenius acids, so they're compounds that produce H3O+. So if we have hydrogen HCl, that's hydrochloric acid. We mix that with water. We end up with so if we remember back to that horrible week of redox reduction reactions, chlorine is reduced, the water is oxidized. Even though it's not an oxidation reduction reaction, we can still classify it as a water. And what we end up with in a solution is not really this. We end up with these HCl. When you put an acid into water, so HCl is hydrogen chloride or hydrochloric acid. When you put it into water, the reason it's an acid is because it breaks up into H plus and Cl minus. And this here is the reason that it's considered acidic. And this H plus is what does all the damage. So if you spill a really strong acid onto your skin, it will burn you really badly. It will eat through the layers of the skin. There are also acids that are bone-seeking. So they will quite literally go into your bones and work their way up through them. So it's this bit here that in hydrochloric acid is dangerous. It's highly reactive. It's H plus. It doesn't have any electrons in its outer shell. So it will just run on through your skin and it will start tearing all the biological bits apart. The stronger the acid, the more of this is produced when it's mixed with water. Hydrochloric acid is really important. Most of your pharmaceutical drugs are, so you would have so the hydrochloric acid on the end in the pharmaceutical drugs allows the codeine or whatever the drug is to be dissolved into water and taken up by the body. If it was just thrown in as the drug without the hydrochloric acid, the body wouldn't be able to absorb it or take it up. So that's an acid. Acid dissociates from its two parts, so hydrogen and chlorine, to H plus and Cl minus. That is an acid, definition of an acid. So Jacob mentioned sodium hydroxide, which is what they would call lye, especially in the US. Very, very strong cleaning agent. Actually dissolve most of a body in sodium hydroxide, in case you're wondering. you would need to use a hydrochloric acid to get rid of the organic, really organic-y bits, and then hydrofluoric acid to get rid of the bones, I think. So, bases, so sodium hydroxide. For the purposes of your sort of schooling years, if it has an OH on it on the end, it's a base. If it has a hydrogen at the beginning, it's probably an acid. Few exceptions. It's got a H here, almost certainly an acid. You've got OH on the end, it's a base. So, same thing, we mix this in water. And it dissociates into and we said that the hydrogen that's produced by acids is what does the damage. This bit here is also what does the damage, but in bases. So it will go along anything that has an exposed hydrogen, so all of the organic molecules in your body, and it will begin reacting with it. Bleach is one of the most common things that is accidentally ingested because it's a clear liquid. And in restaurants, you're not allowed to use clear cleaning liquids anymore. They'll have to be color-coded because people were spraying bleach around eating services, and people can get really sick from bleach. Or sodium hydroxide, or lime, any of the clear fluids. So that's a base. It produces OH minus. Just realized I was screen sharing and I was going through that. So the Lewis acid, a bit more complicated, but we'll go through it anyway. So Lewis acid in this. So remember back to redox reactions, there is, I'll quickly share it on the screen so you can see what I'm talking about. There is an acceptor and a donor of electron pairs. So, skewed my slides again every time I try to present on Google Slides. So BF3, so nitrogen should be minus, donates a pair of electrons to BF3 and it becomes F3B. I might do a quick video on that, how that process works. But the base is the donor and the acid is the acceptor. So if you think about the word that we use, the redox reduction reactions, in that swapping around, so from BF3 to F3B, there is an electron pair donated, which is the Lewis base, and the electron pair accepted, which is the Lewis acid. I wouldn't particularly worry too much about the Lewis. Just remember the Arrhenius. That was just a good example of a different way that we classify them. So, all those acids and bases that we wrote down we're going to plot them on the pH scale, which is the measure of the concentration of H plus or OH minus. So, just to keep it simple, and we'll leave it at H plus. The concentration of H plus. Let's use the chat. Where do we think water sits? So Jacob says pH of 7. So this is what we call a neutral which is pH of distilled water, so pure water. What do you think could be here down to 0? So, yeah, so distilled water is pure water. So any ideas what might be down here? So this is acidic. Any ideas what could be 0? So the strongest of the regular acids. So 0 would be battery acid. So it is 10 million times more acidic . 10 million times more acidic than distilled water. Now this scale isn't a normal scale, it's not linear. So 6, 5, 4. So 10 times more acidic than 7, 100 times, 1,000 times, 10,000 times, 100,000 times, 1,000,000 times, and 10 million times more acidic than pure water. And we can go so 8 is 10 times more basic than 7. 9 is 100 times more basic. 10 is 1,000 times. 11 is 10,000 times. 12 is 100,000 times. 13 is 1,000,000 times. 14 is 10 million times more basic. So it's what we call a logarithmic scale. It's not a linear scale. It's not, well, 0 is 1 times as many. So 1 is 1 times as many. It's 10. Each time gets the concentration increases by 10 on the previous number. And then we have all the 0.1, 0.2, 0.3, 0.4, so on and so forth. It's all related to how much H plus is in the solution. So gastric acid, or the acid in your stomach, sits somewhere between 1 and 3, depending on the person, depending on the time of day, depending on how much water you've got. Lemons sit around 3. Contains citric acid. Stomach acid is mostly hydrochloric acid and other gastric juices. Soaps sit between 8 and 9. Sodium hydroxide up around the 13 to 14, depending on the concentration. What else we got? Examples. Orange juice. Somewhere between here and here. So you can see quite quickly that we go from lemon juice to battery acid, or seemingly quite quickly. So that's how a logarithmic scale works. It goes up, the concentration goes, or the concentration goes, and then it goes straight up to 10 million. So it slowly increases, and then it ramps up in a vertical line. If you watch the coronavirus carefully, you can see that's also how viruses, infectious as a virus, goes on. So, let's take a picture of my beautiful artwork. So, yes, I know I say so a lot, apparently. I can't stop myself from saying so. Sorry. So, I can't say it again. Okay. We have strong and weak acids. If you're following along on the slides, we are on slide number 9. So, I'm going to use a slightly different example. So we have HCl. So it associates completely into H plus and Cl minus. There's no more of the original molecule left. It's all now H plus or H3O plus, because the hydrogen technically binds with the water to create H3O plus. But if we have a weak acid, we have some H plus, some Cl minus, but then we've still got some HCl molecules that haven't completely dissociated. So what the difference is, the concentration of this is higher. That's why strong acids are more dangerous. You can put a weak acid, and again, hydrochloric acid is not a weak acid. I might use a different example, actually. Weak acid would be, wasn't the best example to use. Hydrogen fluoride is a relatively weak acid. So you're going to have F minus, H plus, and then HF still bound together. So strong acid completely breaks up from there. Well, not all of them completely, there is a limit, but the more it breaks up, the stronger the acid, the more of the original molecule left in the solution after it dissolves, the weaker the acid is. So once that slide, let's explain what I did then. So strong and weak acids. And we can demonstrate this because if we look at a weak acid, So HCl is a strong acid. It has a one-way system. So hydrogen chloride plus H2O and this is a one-way reaction. So it's going, putting the hydrogen chloride into the water, it completely dissociates into H plus and Cl minus. Hydrogen fluoride plus water, we get what's called this equilibrium, which means that the reaction so it looks kind of the same, but we have this two-way reaction. So what we end up with is some of this will turn back into this. So the reaction is going forward and is also going backwards. So it's forwards and backwards. Whereas strong acids happens in one way. So we can, if you look at bases, it's exactly the same. So sodium hydroxide plus, it dissociates into dissociate into water. This completely breaks up into these two. So there's lots of sodium and lots of hydroxide. Same as the bases, the more of this that's produced, the stronger the base. Again, weak bases are the same. So sodium hydroxide is a strong base. Weak base may be magnesium. Magnesium hydroxide. We end up with, when we put it into water, keep it consistent, right? H2O. And it produces magnesium. But what happens is the reaction is happening forwards and backwards. So magnesium hydroxide is a weak base because as quickly as it's dissociating into these two from this, it's then reforming. Hi, Cara. I hope you weren't waiting there too long. I'm pretty much near the end now. So we have these things called conjugate acids and conjugate bases. So HCl So we have, if we look at here, HCl is losing its hydrogen. So, keep saying so, make no apologies for it. So, I did it again. Hydrogen chloride loses its chlorine, that would mean it's hydrogen. So it is the donator. So it's the acid. And the Cl minus is what we call the conjugate base. Which, I mean, I won't explain in too much detail, but it's had its acid taken away, or its hydrogen taken away. And it's now the conjugate base. Hydrogen chloride is the acid. Chlorine, because it's lost its hydrogen, is what we call the conjugate base. Again, so when the opposite happens, so when a base accepts the hydrogen, or the H+, so NH3, so this is the base. And the base in this equation accepts one of these hydrogen from the water. And this is now the conjugate acid because it has gained again. I'll do a couple of videos for that. I do have the recorder. I just need to upload them for last week as well. So this is the base. The water has donated its hydrogen to NH3, becomes NH4+. So it's now the conjugate acid for NH3. So if it was, lose an example, NH3, if it's the conjugate acid, you add a hydrogen. So if it's had so in this case it would be NH4+. The conjugate base of this, hydrogen removed. So it will be NH2. Probably be minus as well, NH2 minus. So acid, if someone says, what's the conjugate acid for NH3? You would add a hydrogen for NH and make it NH4. If it was, what's the hydrogen base? What's the conjugate base? You remove the hydrogen. So yeah, again, let's skip past that one because I just explained it. I need to look at the slides when I'm doing it, otherwise I just get ahead of myself. So the final one that we'll look at is what's called a neutralization reaction. And that means that an acid reacts with a base to completely neutralize the pH to 7. So don't try this because it also releases massive amounts of heat. If you mix very strong, if you mix battery acid and sodium hydroxide, you would get injured. So we know that hydrogen dissociates into HCl dissociates into H+ and Cl-. sodium hydroxide, Na+. So what happens here is that they dissociate and they rearrange with each other. So hydrogen bonds with hydroxide and creates H2O. Sodium and chlorine bind to each other and they make tame salt. But you get a massive release of heat. And this is called a neutralization reaction. So the pH is neutralized because you're forming water and salt from these acid and base. That's the simplest one. There are more complicated ones, but they're all based on the same principle, that these acids and these bases dissociate and they rearrange, creating water and a salt. So I think I'll leave it there. I'll keep it relatively light this week. I'll put up some more videos on that and on last week's as well. And I'll see everybody later on in the week or next week.